We present our work on the role of Jacobians in robust manipulation, demonstrating the capability of online estimation of inverse Jacobians for systems with no a priori knowledge. Traditional robot control relies on analytical methods that require precise system models which limit generalization to arbitrary tasks. For instance, applications such as grasping and using a tool require knowledge of the tooltip for manipulation. To avoid the complication of analytical approaches, we directly estimate the inverse Jacobian from online random robot movements in a process we call self-identification, or self-ID for short. We find an approximate inverse Jacobian using a novel framework which separately estimates the signs and the magnitudes of the inverse Jacobian elements. We control arms and passively adaptive robot hands, which both have regions of stability where discontinuities like loss of contact or singularity are avoided. Within these regions, we find a manifold of valid inverse Jacobians based on path following capabilities under random element scaling error. So this valid region is the required accuracy for our estimator. We split the estimation into two subproblems: the signed inverse Jacobian capturing the primary direction of motion for each actuator and pose axis, and the magnitude inverse Jacobian representing the amount of actuator motion for some pose axis movement. Splitting the inverse Jacobian into two parts enables robust estimation with a feasible number of online system samples. We use a weighting system to find the signed inverse Jacobian. The signs of a movement are determined by the actuator and pose change directions, and the weights are based on the relative actuator and pose change magnitudes. As self-ID continues, the weights are summed and the sign for each element with the largest weight is used. This enables accurate sign prediction for complex actuation observation pairs. The magnitude inverse Jacobian for each step is found by the ratio of actuation magnitude to pose change magnitude. The mean value across all steps for each element is the estimate. While the step is inaccurate due to the simplistic approach, it's close enough for a fine-tuning optimization to produce a valid inverse Jacobian estimate, as shown in our experiments. First, we show our estimator performing a handwriting task with a Yo Model O hand. The estimator begins by observing the movements of an object's April tag while making random actuator movements until the system converges to an estimate. Then, the estimated inverse Jacobian is used to trace the phrase grab lab with the April tag while continuing to update the estimate in the background. Next, we perform position-based peg and hole insertion tasks with the estimated inverse Jacobian of a UR5E and Yale Model O hand. First, the arm inverse Jacobian is self-identified and used to move the arm to a predefined grasp position, where it grabs the object. Then, the arm goes to a predefined waypoint above the hole. As the grasp introduces rotational error, the hand uses its estimated inverse Jacobian to rotate the object so it can fit into the hole. Finally, the arm places the object close to the hole and releases.